or is closed? No, sorry. All right, so homework 6B, oh, it's not due Sunday. That's due, oh yeah, Sunday of next week. Today's Tuesday, right? Okay, so we have a midterm on Sunday, and it's covering chapters 4, 5, and 6. It's during the ordinary class time from 8 until 8:50, and I'll upload a formula sheet so you can take a look at it if you want to view it early, and I'll print that out and bring a copy of the formula sheet for you on the day of the exam. Okay, so are there any questions related to the announcements?
It's not May 1st,
Same day as the midterm. Yeah, Sunday, May 8th. Or Sunday, May 1st. Yeah, let me clarify it. I mean, I don't know why there would be a delay, but May 1st, as it says on the schedule. All right. Other questions? Yes. Yeah, the final exam is comprehensive. For the final, there will be an emphasis on the material that was covered since exam 2, but in this course, the material is sort of naturally cumulative, and so you should be prepared for anything that we've taken during the course. All right, so today we're going to be talking about nozzles, but before we do that, let's just sort of refresh our idea about how to solve momentum problems by looking at this black box. There's something going on inside of the black box that is changing the direction of the flow streams. And from the perspective of the forces required to hold the system steady, it doesn't matter what's happening inside of the black box. It may be that somehow the jets are running into each other in a magical way, that these two streams coming in then deflects it coming out. Obviously, it's not going to be magical. There's probably a series of vanes or valves in there that's redirecting the flow. And so it doesn't matter if it is a vane or a nozzle or whatever the case may be, but what you should always do for a problem-solving strategy is to put a control surface around where fluid streams are changing direction. And as long as you do that, then you can say what's happening inside of the control volume is going to need some external force to hold the system steady, and that's what you're solving with the summation of forces in either the x direction or in the y direction. Okay, so in this case, what we are interested in, we have a stream coming in at location 2 and location 4, and maybe just by looking at it, you can see that these two streams are going to cancel each other out, because remember, momentum is the mass flow rate times the velocity. Now, we're given the volumetric flow rates here, but since it's all the same liquid in all 4 streams, then the volumetric flow rate and the mass flow rate is going to be proportional. So look at stream 4 versus stream 2. In the x direction, you see that you've got 60 meters per second and 0.15 cubic meters per second. And then down here you have double the volumetric flow rate and half the velocity. So we'll take a look at that numerically, but just sort of by inspection we can see that if you have one stream entering from the left and one from the right, and this has half the velocity but double the flow rate compared to the other stream, we should see that there's no forces in the x direction required to hold the system steady. All right, now have a look at stream 3. The flow rate isn't specified, and so how are we going to get around that problem? Because we need to know the volumetric flow rate so that we can find the mass flow rate. Right, so we have 2 streams coming in, 1 going out, and what's left will exit at 3. Now, that assumes, of course, that whatever is happening inside of this black box does not include accumulation. And so it's not explicitly said in the problem statement one way or another, so in our solution we can say, assuming that there's no accumulation. And that's a fine assumption to make in this case. All right, so let's go through these steps. So let's first of all solve this in the x direction to find out what is the force required to hold the system steady, and our first look at the situation tells us that the force should be 0. So in the x direction, we're going to find out the forces, and in the y direction. And so this will sort of be the sort of thing we've seen several times before, just to refresh our memory on momentum. And then we're going to take a look at nozzles, which is quite a bit more interesting, I guess we could say. All right. At the top is the information that we're starting with, and if we apply things in the x direction, you'll notice that there's only in. There's no outflow in the x direction. And so that means that the first set of terms here is going to be just omitted from the equation when we start substituting things. And so we can calculate the mass flow rate at 2 and at 4. And then this is how we begin for the substitution in the x direction. We have stream 4, and we're subtracting that because it's an inflow, times velocity 4. And then subtract mass flow 2, velocity 2. And the subtract because it's still in the second half of this equation. And I haven't yet substituted in the directionality of the velocity. This is just assuming some velocity, and then when I actually start substituting the numbers, I'll also put in the sign of those numbers. And so when we take that approach, we get that the force is 0 because the two streams are canceling out. Here we have negative 300 times 60 plus, because minus and a minus sign there, 30 times 600. And so the forces in the x direction cancel each other out, just sort of like was our suspicion from looking at it initially. Any questions on the first part and what the procedure should be? So we're going to take the same approach when we look in the y direction, except for it's going to be forces in the y, momentum out, velocity out in y, momentum in, velocity in y. So in the y direction, we only have flow out, which means we'll only have this first term. There won't be the second term. And so we're going to have mass flow rate 2 plus times velocity. Well, I guess we'll just scroll down to it. All right. So finding each of the mass flow rates, and mass flow rate 3 we get through the continuity relationship. That is, that the flow in has to go somewhere. Some of it goes out one of the directions, so that means everything else has to go through the mass flow rate 3 stream. So here you can see the equation. The whole second half is 0 because there's no flow rates in the y direction, only flow rates out. So there's the two components of it, component 1, component 3. Just substituting in the mass flow rate and the velocity, and it's positive 20 meters per second because mass flow rate is up in stream 1, and then this negative 15 for the velocity at 3 is because that stream is down. And so I've calculated the numbers for both of these, 4,000 newtons and negative 10,500, just because sometimes I like to see, like, the final answer, where are the different components coming from. So let's think about this. It's saying that we have to push down with a force of 6,500 newtons to hold the system steady. So let's scroll up here, maybe to the original. And so it's saying that a net force down has to be applied. We would have to push down on this black box to hold the system steady. And the reason for that is because so much more flow is going out through 3 than going through 1. You've got 700 kilograms per second going out downward. And so when you have a stream that's changing direction, for instance, we had in the homework a vein that was redirecting the flow downward like this. So if you have a stream coming in horizontally and you want to change its direction so it has a downward component, You have to apply a force in the direction that you want the change. And here, the net change is you've got more flow going down than going up. And so you've got two streams coming in with no y component, and you want the majority of that flow to go downward, and so a force that's downward has to be applied, a net downward force. And so that's when we go back to the final answer here. I hope that you can tie together the numbers and then sort of the conceptual sense that it should make and the reason and the logic behind it. Any questions from this example? Good, yeah. So here is where I did it. I said the idea behind M3, and this expression is that in equals out, because M3 and M1, if you take that over to the other side of the equation, M1 and M3 are my terms that are the out, and so I'm saying the flow out is equal to the flow in. So M4 and M2 is the flow in. So I'm saying in flow equals outflow, and that's the Reynolds transport theorem, which gives us continuity, just saying that there's no accumulation inside the black box. All of the flow that goes in has to go somewhere. So everything here was given. We had all the flow rates, Q4, Q1, Q2, but we didn't have a Q3. So Q3 is just everything else balances into Q3. Are there other questions from the example?
When you deal with water, it doesn't matter if you dealt with cubes, solid, or mass flow rate?
No, it does matter, because if you want the units to work out, then it should be in terms of kilograms per second. And ordinarily, when we're dealing with Q, our typical thing would be to have cubic meters per second. So you'd be off by a factor of 1,000 if you didn't make the conversion between them. Okay, so now we're going to talk about nozzles. Now, this drawing is implying a couple of things, and before we start thinking about the specific calculations here, let me just sort of explain how we handle this. We have flow coming into the nozzle, and so the pipe continues to the left, but it's not showing that. So imagine that we had a control surface that cut this pipe, and so this isn't a physical break in the pipe, but it's just we're only showing what's on the inside of a control volume. And so to the right, then this is actually a jet of water that's exited the nozzle. So you can see the black line is denoting the physical pipe surface, and then suddenly there's no more black line. That's because the water's spraying out and there's a jet there. So since there's a pipe on the other side of our control surface, we can think of it as that there's a pressure on the outside of the control surface. And the pressure in the pipe is pushing on whatever's on the inside of the control surface towards the right. And so if I was going to sort of modify this drawing, I'd say that there is some pressure pushing on the control surface here, because the pipe itself is pressurized. It's full. You can see that the pipe is full, and there's enough pressure here that it's causing a jet of water to stream out. And so here is some pressure pushing on a pipe, and in fact, this pipe, we have a diameter given, and so we could calculate from that a certain cross-sectional area. And you may remember that force is pressure times area. And so the direction we're going to be heading in this example, over here on the left side of the equation, it's saying the sum of the forces required to hold the system steady, right? Now, you can see that there is a flange here. And the purpose of this flange is just to give you a place to grab onto the nozzle. It's a connection point or an attachment point so that you can apply a force. Otherwise, it would be very hard to grab onto this pipe section because of how it's smooth. So it goes all the way around. It's a ring. It's sometimes hard to think about when you're seeing a cross-sectional view that the object has 3 dimensions. And so this is a circular pipe, and this ring just goes all the way around the pipe, and it wouldn't matter whether it went all the way around or if it was literally in 2 points. because in this equation what we're going to be calculating is just the net force required to hold the system steady. So this formula doesn't take into account if there are 2 places that force is being applied or if it's being applied at 3 places. It's just saying based on the momentum and the flows and the velocities, how much force do we have to apply to equalize the system, to keep it so that it's not beginning to accelerate. So what I'm saying is there's this external force that's being applied to the pipe, to the water on the inside of the pipe. It's the pressure times the area. And then also, in addition to that, P times A, then there's the net force that we apply at this flange to hold the system steady. So there's 2 things that we're going to be solving for in this example. Okay, so now with that said, we can take a look at the specifics of the problem statement here. We have the volumetric flow rate is 0.3 cubic meters per second, and it discharges into the atmosphere. And because of it discharging into the atmosphere, that makes it easier for us to solve a few things, because we know, for example, that the velocity can be calculated using Bernoulli's equation. What we're going to do, you can see they've already labeled location 2 and location 1 in the drawing. And so here at location 2, since the stream is surrounded by air, the pressure of the jet is equal to 0. So we're going to say that P2 is equal to 0 when we start using Bernoulli's equation. And the reason why we need Bernoulli's equation, again, is because we have to find out what is the pressure inside the pipe. Because we need to know the pressure inside the pipe, because it's as though there's a force pushing on whatever's inside of the control surface here. So let me outline for you what our solution strategy is going to be. First thing that we need to do is just sort of calculate all the preliminary information. So for example, what is the mass flow rate is going to be one of our preliminaries here. They say it's water, and we're given the volumetric flow rate, so the mass flow rate should be easy. We're going to want to know A1. We're going to want to know A2, because right now the diameters are given, so we can calculate the cross-sectional area from that. The continuity equation is going to allow us to find V1 and V2. And when I say continuity equation, what do I mean by that? Q in equals Q out. Exactly. So if we look at this section, it's an enclosed nozzle, and there's no place for storage right now. It's already full of water, so if 1 liter goes in, 1 liter has to go out. So Q in equals Q out, or if we say it in terms of A1 and V1, what's the relationship? A1 times V1 is equal to A2 times V2. So with that, we can calculate the velocity at both locations. All right, and then our next step will be to apply Bernoulli's. And with Bernoulli's equation, we're going to find out the pressure at 1. And then finally, we're going to apply momentum. And from momentum, we need to use this expression. So the sum of the forces in the x direction are going to be the sum of the mass flow out, velocity out in x, minus the sum of the mass flow rate in, velocity in x. So that's easy enough. But what will be different is on the left side of the equation, we're going to have P1 A1 plus F sub x. And F sub x is how much we have to push on this connection point, either to the left or to the right, we don't know yet, to hold the system steady because of the change in momentum. So here we have the same mass flow going in and out. M dot in equals M dot out, but the velocities are going to be different because of the way the nozzle is shaped. Okay, so over here on the whiteboard you've got the steps that we're going to go in. Find the preliminary stuff. Use Bernoulli's equation to find the pressure on the inside of the pipe. And then once we know that, we'll substitute everything into momentum to see, what we're really trying to find is this F sub x. That's the unknown in this problem. Determine the force required at the flange to hold the nozzle in place. Always start with a sketch, right? I'm going to keep giving you that advice the whole semester, and then you can forget about it during the summer. But here's my sketch, and I tried to make this sketch so that it was obvious that you have a pressure acting over an area. So I did some attempt to give it an oblique view where you're sort of getting an angle there and can see that it's, and just to reiterate what that is it's the water on the outside of the control volume is pushing on the water that's inside the control volume. So our system that's being held steady by the force at the flange, our system is the fluid that's inside of the nozzle that's inside of the control volume. So this pipe continues to the left. It's just we cut the pipe with the part of the system that we're considering. We can't consider the pipe out towards infinity. We're just looking at the section that is concerned with the change in velocity. So with those preliminaries here, we find the mass flow rate based on the volumetric flow rate and the density of that of water, and then the cross-sectional areas for both 1 and 2. And then you can see it's with continuity equation where we say A1 V1 is equal to A2 V2, or just we can find the velocity at 1 and the velocity at 2 using the cross-sectional areas at both locations. All right, so here's the rest of our strategy here. We use Bernoulli's equation to find out the pressure on the inside of the pipe, and you've done that before, where we're starting with some jet, and the advantage of a jet is since it's touching the air, you know the pressure of it. And this one was horizontally oriented, which means that we get to cancel out the Z1 and the Z2 because they're equal. And so then if I rearrange this in terms of the pressure at 1, and of course this term is the density, that's not a P, that's the density, and then it's the difference in velocity. So that's why, here, in this nozzle, the mass flow rate's the same. But the reason why we're going to have to apply an external force is partly because of the pressure and the area thing, but then it's also partly because the velocity is changing inside of the nozzle. So here, the V2 squared minus V1 squared, it's the difference in velocity that's causing the pressure, and it's also the difference in velocity that's going to require external force to be applied to hold the system steady. Okay, so here you can see that when we substitute all the values and do the calculations, the pressure at 1 should be 720,000 Newton per meter squared. And then here is the momentum equation, and you're going to have to do the same thing for the homework. You've got a homework assignment due on Sunday where I think 2 of the problems are nozzle problems like this. And so you need to look at the diagram, and where you have a pipe that's cut by the control surface, you have to say, I need to account for the pressure and the area as though it's an external force. You think about it as that pressure times area is pushing on the system. So here, the pressure times area is pushing on the system to the right. If it had been pushing on it to the left, I would put a negative P1A1 there. But the direction of the pressure is towards the right. And then the force in the x direction is what we're trying to calculate. And then I have simplified m dot, because mass flow rate out and mass flow rate in is the same. I just have a single m dot there. So it's out minus in. And then you can see I've rearranged and substituted the values. So the momentum part of it means that we would have to apply a force to the right in the amount of 10,000 newtons. But the pressure times area part of it is the opposite direction. It means that we would have to push to the left to resist that. And I suppose that makes sense, right? You think about this flange. We're pushing on the flange to resist two things, to resist the momentum and to resist the pressure times the area. So the pressure times the area, obviously, if that's going to the right, then we would need to push to the left to resist that. But then it's the opposite way for the momentum part of it. The momentum part of it says that we've got a fluid accelerating, and so we need to push to the right to cause that fluid to have a higher velocity in response to it. So the net effect, we would push to the left. And so you'll notice the way that I'm describing the directionality of that force, I've got the negative sign, and in my drawing, I show the force is to the right. So a negative of that means the force is to the left. And just to remove any doubt about the direction of the force, here in the margins I've said the external force must be applied to the left. So I'd encourage you to do the same thing. It's too easy to get mixed up about what direction the force is. And so, the three ways that you can specify the directionality of the force is with, the sign convention, with drawings, and then clarifying any potential conflict between the two with just the text on what force is required and whether it's holding the system steady or whether that's the force of the jet on the object itself. All right, so here is one of your homework problems. You've got a pipe bend, and the first thing I should mention is the drawing that they provide, it's a top view. So you're looking down on this pipe bend from above. And the reason why it matters is that they, I believe, tell you the volume of the water that this bend can hold. And so one of the force components that you're going to have to apply is the weight of the water and the weight of whatever steel exists in that pipe bend. Okay, so that's one aspect of it. But then what you can also see is that there are going to be forces in the x direction that have to be accounted for. So here you've got the flow entering the bend from the left, and it's exiting towards the right. Now we're going to have the same thing with the pressure and the area on this, like we did in the example that we worked today. But what's tricky about this, they're trying to confuse you. They're trying to see if you can figure it out. You've got the flow in here and the flow out, but that doesn't affect the direction of the pressure and the area. So for both of these, there's a pressure that's pushing to the right. The pressure on the outside of the control volume is pushing to the right. So even here at 2, even though the flow is exiting the nozzle to the left, the water that's on the outside of this nozzle is pushing to the right. And so when you're solving that problem, if we were going to expand the equation like we had here we had P1A1 plus f of x is equal to the momentum aspect of it. On the homework, you're going to have two such pressure times area components. And so you're going to have the pressure times the area here towards the right, plus the pressure times the area there to the right, plus whatever external force has to be applied at the system of flanges. So there will be three things on the left side of the equation, and then on the right side of the equation is we're keeping track of the mass flow rate out minus the mass flow rate in, multiplied by the velocity of each of those, of course.
The force we find for the flange is going to be divided by 2.
No, because we're not asking how much is applied at each one of these. It's just asking what's the total external force that has to be applied to hold the system steady. I mean, in the problem statement, if it does say there are 4 flanges, what's the force per flange, then you'd maybe divide by the number that's shown, but it's really just asking what's the net force required to hold the system steady. So don't be thrown off by a cross-sectional view of a circular object and that's a ring and there's 2 rings. It's usually just asking the overall force. And you have another one that's similar to this, where I think it's a T section. And so the pipe is being cut in 3 locations. 2 of them are in the X direction, 1 of them is in the Y direction. But, I mean, once you've seen something like this, and you have already accounted for the pressure times area as an external force, then it doesn't matter how many pipe sections are cut. You just treat it as though it's some external force. So that's all the time we have for today. Remember, on Sunday we've got an exam, and I'll post the equation sheet for the exam online in case you'd just like to glance at it before the test. And then also on Sunday, the next homework's due. So if you have questions on the assignment, feel free to pass by my office. Over the weekend, you can send me emails, and I'll do my best to respond if something comes up. So I'll see you next week.